Welcome back, everybody, to the Python tutorial seminar series. Today, Dr. Kevin Paul will be covering object-oriented programming. Before I begin the lesson, I need to review the code of conduct. By joining the Zoom call, you've agreed to engage in respectful communication and adopt these values. Any inappropriate remarks will have you removed from the call by a co-host. As usual, the seminar is designed to be an hour long, so we do not have time to stop and give individualized attention. Co-hosts will be available to help you in the chat, but if your issue is more involved, we might need to set up a meeting to catch you up at another time so that you're able to get the most out of the next seminars. Your speaker today is Dr. Kevin Paul. He is a computational physicist and software engineer working in the Computational Information Systems Lab, or CISL, at the National Center for Atmospheric Research. Dr. Paul is the head of the experimental development team, Xdev, and is passionate about open source development and teaching Python to Earth system scientists. Today's learning resources I'd like to share with you are, as usual, Stack Overflow, always a good place to get help. The question you have has probably already been asked. And today's content, which is on Kevin's GitHub, and I will post the link to that in the chat in a second. And with that, I will hand over the reins.
Thank you, Julia. I will share my screen here. Okay. I hope that everybody can see this. If not, please speak up and let me know. Welcome to our next Python tutorial seminar. Today, I'm going to try and give a practical guide to object-oriented programming in Python. There's a lot of content that can be presented when talking about object-oriented programming. And I'm not going to have time to go into all of the theory, things like design principles, design patterns, the deep theory and comparisons between object-oriented programming and functional programming or procedural programming, or any of that. Instead, I'm going to focus on what objects are, how you use them, how to create objects of your own, and perhaps most importantly, at the end, I'm going to talk about when would you ever want to use object-oriented programming yourself. If you're following along, you can scroll down to the bottom of each page and click on the next or previous buttons to navigate through this tutorial. So let's start with what is an object. To computer scientists, an object is something that groups together data and functions. It's that simple. That means for the most part, object-oriented programming is really just a way of organizing your data, or I'm sorry, organizing your code in a way that makes it easier to maintain, debug, understand, and hopefully scale. That is as your code base gets larger, not the parallel programming sense. Now, the reason that this is important in Python is because everything in Python is an object. And if you don't believe me, I'd like to introduce you to the dir built-in function in Python. If you've never used this, what this function does is it takes an object that you pass into the function, and it prints out all of the attributes contained by that object. Those attributes are either data or functions. And try it out. If you're following along, take a look and see what the dir of a string is. This will list out all of the attributes attached to this object. Now you'll notice that some of these attributes have names that start with double underscore. And many of those, in fact, I think all of those double underscore starting names also end with a double underscore. Any attribute that starts with a double underscore in Python is private, and I'll talk about what that means a little bit later. And anything that both starts and ends with a double underscore is not only private, but it has special meaning. And I'll talk about those special methods later as well. But when you look at the ones that don't start with an underscore, you should see a number of things you're probably familiar with. Names you're used to seeing, like capitalize. Capitalize is a function that you can use on a string that capitalizes the string. There's also lower to make it lowercase, and there's upper to make it uppercase. Split takes a string and splits it into a bunch of substrings, and so forth. There are a lot of attributes attached to this object, this string object. But did you know that Python, as I mentioned already above, everything in Python is an object, and therefore numbers are also objects. This is different from many other languages where numbers are treated as primitive data types. But even a number like 1 in Python is an object, and you can see that it has a lot of attributes attached to it. Did you know, for example, that you can get the imaginary part and the real part of any number in Python? Try it out. Take some time right now and see what dir gives you on a list, a dictionary, and maybe even a function. In fact, if you want to be super meta, you can do dir of dir and see what that gives you. I'll give you 30 seconds to try that out with a couple different things and see what it gives you. Okay, did you see anything that you were familiar with? Did you see any attributes that you already have used before, that you already recognize? Did you try the meta dir and notice that even a function is an object in Python? Dir is an excellent method to explore the contents of objects in Python. But it's not the only way of exploring the contents of objects in Python. Jupyter itself provides an excellent mechanism called tab completion. To do this, all you need is an object. In this case, I'm going to create a variable called I, which is a number. And now to actually explore it, I just do I dot, and then I hit the tab key. And you should see a little window pop up giving you the contents of that object. Now there's a bug in Jupyter that doesn't fully render the window. So if you do it a second time, you'll see it fully filled in with all the colors. The nice thing about Jupyter's interface here, the tab completion window, is that it not only gives you a list of attributes contained by this object, but it tells you whether those attributes are functions or instances, in that case, data. And it even color codes it, blue for function and orange for instance. And you'll also notice that any of those private attributes, the ones preceding with names preceding by a underscore, those are not listed. Jupyter respects an object's privacy, and it doesn't show things that are meant to be private. Okay. That's how you explore the contents of an object. Now, how do you use the objects? Fortunately, you're already probably familiar with this because, as I said, everything in Python is an object. So you've probably interfaced with many different objects before, but one of the most common ones you're probably familiar with are modules. Anytime you import something, you are creating an object. I'll do an example down here. I'm going to use the write file Jupyter cell magic to create a file called mymodule.py, in other words, a Python module. And I'm going to create in that file an X variable, and I'm going to define a function F that returns a string called hello. Execute that cell, it writes it to a file, and now I can import that module as I'm familiar with. To get the contents of this module, then all I need to do is use dot syntax. So in other words, to retrieve that X variable, all I would do is mymodule.x. To get the function F, I do mymodule.f. And then if I wanted to call that function, I would just obviously add parentheses after. And that's it. That's something you're already familiar with, but maybe you didn't realize that what you were doing when you were accessing the contents of a module was the same thing you would do to access the attributes of any object in Python. So now let's get on to how you actually create an object, how you actually use this in practice. But before we can do that, we have to define some terminology. Classes and instances in particular. Classes are the blueprints for creating your own objects. Instances are the objects that you create based on those blueprints. So if you think about it, there's really only ever one class, there's one blueprint, but you can make many real things based on that blueprint. Those are the instances. To define a class, to create, all you do is you create a class block, like illustrated here, that starts with a class statement followed by the name of the class that you, or the name that you want your class to have. In this case, I'm just creating the name my class. You'll notice that it's capitalized. That's pretty much a convention in Python to capitalize class names. And I've created the contents of this class block to be very similar to the module example that I did before. I have a variable X, and I have a function called setY. I'll talk about the contents of that function and how that function works in a little bit. But to declare this class, just execute that code. And now I can create an instance of that code by calling the class, in essence. Using the class name followed by parentheses, if I execute that, it returns a new instance, which I'm calling MC, of my class. Now that I have this class and I have an instance of this class, I can explore its contents. The first thing you'll notice is that this variable X is owned by the class. In other words, X is defined in this block, in the class block, and therefore it's owned by the class, which means I can access it directly from the class itself, like so. Notice I didn't have to access it from the instance. I accessed it directly from the class. That's true for the functions in there as well. SetY is a class-owned function or a class function. That's typically something we call a method. This method can then be directly accessed from the class too. And what you'll notice about this method is that it takes two arguments. There's this first argument, which I've just called self, and the second argument, y, which based on the name of the function, is probably the value of y you want to set y to. Any method of a class assumes that the first argument you set in it, the first argument of that method, is an instance of the class itself. That means in order to call this function like this, I need an instance of my class passed in as the first argument to the method. Fortunately, I have one. I defined one just up above called MC. And so I can call this function setY, this method, like so. But this is messy. and it's not very Pythonic. The reason I say it's not very Pythonic is because most of you probably know that Python doesn't care, and it actually encourages you to not care very much about what the actual type of an object is when you pass it around. But this way of calling this function requires that you know that MC is an instance of the myClass class. So that's not terribly Pythonic. Fortunately, Python gives you a better way of calling this, and that's down here. You can access the setY function directly from an instance instead of directly from the class. And when you do that, the self argument, that first argument of the method, will be implied. In other words, you don't have to supply it. And this line, which is much more straightforward, much easier to read, that line does exactly the same thing that this previous line did. So now let's actually look at this setY function and see what it's doing. Now that we know that the first argument to setY has to be an instance of the class, the second argument is the value that we want Y to be set to. The function itself, what's actually being done is really straightforward. All it's doing is it's creating a new attribute called Y on the instance itself. And it's setting that attribute equal to the value I pass in, okay? So this line that I just executed before should be creating the attribute Y on the instance MC and giving it the value 8. So if I execute this next cell, it should give me 8. And it does. But what happens if we try to access Y before we call setY? Well, let's try it out. Let's create a new instance of the class. And now let's try to access Y. We haven't called setY on this instance yet. And sure enough, it says there is no attribute Y. By calling setY, we not only set the value of the attribute Y, we create the attribute at that time. But now, after we've called setY on the instance, we can actually access it. And the important thing to know here is not only is the Y attribute being set on the instance, but it is actually completely unknown to the class itself. So if I try to access Y from the class, I get a no attribute error as well. Now the next section here can get a little hairy, so I apologize if this is a little confusing. But we're going to talk about what happens when you change class variables, that is, variables owned by the class itself. Recall that this X variable was accessible directly from the class. It's a class variable. But X is also accessible from instances of my class, like so. The reason this works is because the instance gets a pointer to the class's X variable. In other words, it's pointing to the same location in memory. In other words, these aren't two separate variables that happen to have the same values. This is one single variable owned by the class, and the instances variable is pointing to that same place in memory. That means if I change the class's variable to a new value, the instance X is changed also. And that's again because the instances class, the instances variable points to the same place in memory as the class variable. And because the class is the blueprint for creating new instances, when I create a new instance, in this case MC2, it gets created with the newly modified value of X. But what happens if I change an instance's value of X? In this case, I'll change the second instance to 9. The class value doesn't change, nor does the other instance's value of X change. Only the instance I explicitly changed is modified. The first instance, that X points to the class's value, but the new instance, I have actually changed it to point to somewhere else. This may be confusing. I don't mean to confuse you on this. Maybe it takes some time to kind of absorb this. But the key takeaways here are that variables and functions defined in a class block are owned by the class, but they can be accessed directly from any instance of the class. And any variables or functions defined on an instance of the class are owned only by the instance. Okay. The next thing I want to go back to is what we encountered when we first used that dir built-in function. You'll remember that there were a lot of attributes that started with the double underscore and ended with a double underscore. And I mentioned at the time that those were special attributes. Well, those are special class methods that are part of the Python data model. And those methods actually give special functionality to the class. If there are a lot of these, okay, and I don't have time to actually go over all of them, I strongly encourage that you read in the Python documentation more about the Python data model to learn all of these different things, all these different special methods. But I will talk about a couple of them here. The first one, which is the one you'll most commonly see used, is the init method. It's double underscore init double underscore. Just like in the previous example, when I created the setY function, if you remember, the Y attribute didn't exist on the instance until I called that function. And so if I tried to access Y before calling that function, I'd get an error. If I wanted to prevent that from happening, I could use the init method to create that attribute at the same time that I create the instance. That's what init does. So you'll notice this new class, my class 1, has an init method that looks exactly like the setY function. And what that allows me to do is instantiate, create a new instance of this class and set Y at exactly the same time. So you'll notice I pass in Y when I create the instance, and it's set. So now I'll never have an error where Y is not set yet. There's also a string special method, the str special method. String is a function in Python that allows you to take any object and convert it to a string. If you've never done this before for a generic object type, what you typically get back is something that looks like this. It's not terribly informative, doesn't tell you a lot about the actual object. But if you wanted to customize what that string output was when you tried to pass the object into the string function, you could do that by creating your own str method, special method. In this case, I'm just going to return this string every time the object is converted to a string. So I create an instance, and sure enough, when I try to convert it to a string, that's what I get. All of the special methods in the Python data model do something like this. There are special methods for giving your objects the ability to apply rich comparison to, so greater than, less than. There are special methods to allow you to compute the length of a custom built object, or to see if something is in the custom object, however you choose to define that, or even to give it dictionary-like key value access, or even to do arithmetic with it. There are special methods you can add to your own objects to give them this type of functionality. And I wish I had time to go into all of that, but I don't. So I will just encourage everybody, please read up in the Python data model in the documentation. Now, the last thing you need to know for creating your own objects is, excuse me, it's a concept called inheritance. Inheritance is essentially the ability to create an object, to define a class that inherits all of its attributes from another class. It's easier to understand this from an example. So let's imagine that I create a parent class. I'm going to literally call it parent. I have an init method in it, excuse me, where I pass in the value of x and I set a private x attribute from the value I pass in. I have a getX method that just retrieves that private attribute's value when it's called. And I have a whoami function that just returns a string saying I'm the parent, basically. Now what I'm going to do is I'm going to create a child class that inherits from parent. To do that, I do the same thing that I did before, but after the name of the class in parentheses, I put the name of the class I want to inherit from. And in this class, I've defined an init method that is different from the parent. So in this case, I can pass in x and an optional y value. And you'll notice in that init method, there's this line, which is essentially Python's way of saying, call the parent class's init method to initialize x, basically. And then after that, I initialize the private y attribute in this child class. I don't have to create a getX method because I inherit that from the parent for free. But I can create my own methods, any new methods I want in the child class. And so I'm going to create one for y that's similar to getX. And then I can also override methods from the parent in the child. And in this case, I'm just going to override the whoami method so that it prints out something that's more informative. Now it says I'm actually the child when called. Now I can create an instance of this child class. I give it a value of x equals 1, y equals 3, and I can call getX on that child instance because getX I get for free from the parent. I can call getY, and there are two whoami functions, if you remember, one in the parent and one in the child. And so when I call this, I get the one closest to the instance I've created. Since I've created an instance of the child class, it gets the child class's version of that function. What this is doing is what inheritance gives you is the ability to extend and modify code without having to start over and rewrite it from the beginning. So if someone else has code in a class, you can create a slightly modified version of that class, but either by changing the way that that class behaves or by adding new functionality to it. It's incredibly powerful. And it is the one aspect of object-oriented programming that is not just a way of organizing your code. Private attributes, as I mentioned, are these attributes that start with a double underscore. And when I say private, what this means is these attributes are only accessible from within the class in which they are defined, okay? So if I scroll up to see these two classes that I created, the private X attribute is only accessible from within the parent class. And in the child class, the private Y attribute is only accessible from within the child class because it's defined in the child class. If you try to access a private attribute anywhere else, like from an instance directly, you'll get a no attribute error. And it's really important to understand that these private attributes, even if a class inherits from another class, that child class doesn't have access to its parents' private attributes. For example, so imagine we create a child2 class that inherits from parent, and I've got two methods that both try to get the value of x. The first one, which I've called break me, actually tries to get the private attribute x directly. And the second one tries to get the value of x by calling the public getX method. I can create an instance of this child2 class and try it out. Sure enough, calling break me gets a no attribute error. But if I use the public method, it works. What this represents is essentially something called encapsulation. Encapsulation is the idea where I can hide some data in a class and force other people to interact with that data via only public attributes. It's a way, for example, of hiding fragile data, say data that could be modified and then break everything. It's a way of hiding complex data that could just confuse the user. It's also a way of hiding something that is maybe not performant away from the user. And so later on down the line, when you get around to it and you decide, I want to make that faster, and it requires a massive change to that data structure, your end users never see it. Encapsulation is incredibly powerful. There's also, now we've just talked about private variables. I also want to talk about hidden variables. In Python, any attribute whose name starts with an underscore is considered hidden or private. If it starts with just one underscore, it's hidden. And by hidden, it's actually still accessible. You can still get to it and you can still use it anywhere, just like you would any part of the public. But that single underscore is in some ways the developer's way of saying, use this at your own risk. It could change in the future. So this is a way of letting people know, please don't touch this. This could be fragile. Hidden attributes, as well as private attributes, are actually not displayed by Jupyter Notebook's tab completion. That's something to note. Okay. We've gone through now, practically speaking, everything you need to know to actually create your own objects. But now the important question remains that I'm going to spend the rest of this tutorial trying to answer is, when would you ever want to use object-oriented programming? There are a lot of cases where it's useful. There are no cases where it's required. But one case where using object-oriented programming could be useful to you is when you have complicated data structures. Now, in order to explain that, I need to explain what I mean by complicated. And when I say complicated here, I mean if you do print data and you pass in your data structure to print, if the output of that does not give you enough information to fully understand everything in your data structure, you have complicated data. It's really that simple. If you can't just look at the data structure and say, I get it, and not have to guess, you have complicated data. Let's consider an example. I'm going to imagine an instrument out there that measures a bunch of different variables. And It measures these variables at irregular intervals, different times that is, and it records them all to something like a comma-separated value file, like this. So each line in the file is a record. The first value in that line is the name of the variable. The second value is the timestamp in some weird unit. And the third is the actual value of that variable. And so each line in this CSV file is a new record of some variable. Now, what I'm going to suggest is that we read this data in to a relatively complicated data structure, okay? And to understand what this data structure is going to look like, what I'm going to do, I'm going to tell you what I'm going to do is I'm going to read each record in, that's each line, and I'm going to create a dictionary, an item in a dictionary that corresponds to the variable. And then I'm going to append to a list the tuple, the time value tuple. And by doing this, I'm going to end up creating a dictionary of lists of tuples. Just saying that is complicated, but it'll make sense if you actually read the function here that I've written to actually read this data file. You can see it's just looping through the file. It's reading each line, breaking each line up on commas. So I get the variable name, the time, and the value of that variable. And then it's appending the time value tuple to a list in a dictionary, okay? And so I can now just call that function on the file I created and create my data structure. And now let's try the print data test. As you can see, we've created exactly what I said we were going to create, a dictionary of lists of tuples. And most of this is pretty easy to interpret. If I hadn't told you everything that we were doing beforehand, would you have known though that the first item in each tuple was the time? You might have been able to infer that one of the items in these tuples had something to do with the variable, but would you know which one? Would you know that, for example, the lists don't have to be the same length? In this case, it's pretty obvious, but there's implied information that just looking at the data structure doesn't provide. And that makes the data structure fairly complicated. I'm not saying it's wrong, I'm just saying it's complicated. So now you can imagine creating a bunch of functions that you use with this data structure to compute new things. For example, you might want to plot a variable from this data structure. And to do that, you might need to extract out the time and the values into their own lists. So I have a function to do that. The time pulls out the first element of each tuple, and the get variable function pulls out the second. You can try that out on the variable a, and it gives us something reasonable, what we would expect. What we've done here is we've essentially encoded our knowledge of the data structure into these functions. If the data structure changed, I'd have to change these functions too. Now we can also imagine doing something like computing an integral based on the trapezoid rule, for example. Yeah, perhaps you don't trust me, but this is an implementation of the trapezoid rule in Python using lists. And I can define that, and I can call it just like I did these other functions up above and get the integral of the variable a in time. Can you see, looking at this, any problems that might arise from having this set of functions and this complicated data structure? Well, the way I typically look at it is from two different perspectives. I look at it from the perspective of the data, and then I look at it from the perspective of the functions themselves. If you look at it from the perspective of the data, what the user is being asked to do is hold on to this instrument data structure and pass it around from function to function to function every time they want to compute something. But there isn't enough information in the data structure for the user to know what it fully represents. So it's a bit like being given a lockbox and being asked to deliver it to a bunch of other people who have the keys to the lockbox. And if you had to do that and you weren't at all curious what was inside the lockbox, you're a very different person than I am. There's a problem there that you're basically putting the onus on the user to carry around something that they don't have enough information to modify or use directly themselves. That's the data perspective. Now, from the function perspective, you look up here and you see, well, let's just read this function. If I didn't know anything about what this data variable was, could I understand what was going on in this function? I might be able to look at the function and reverse engineer what that data object was, but it's annoying. And it would be great if I didn't have to do it. So from a function point of view, the fact that that argument being passed into the functions is complicated makes just understanding what the functions are doing complicated. So is there a way out of this? Well, one way is to recognize that the data and the functions are intrinsically related to each other. And so why not group them into a class of their own? I'm going to give, there isn't a lot here, but I'm going to give everybody 5 minutes to try that on your own at the bottom of this cell. And when you're done, we'll move on to the next notebook and see how I solve the problem. Feel free to ask any questions in the chat if you would like, and we'll help you out. Okay, we're at the 2-minute mark. How's everybody doing? Questions? If you want, you can pose them in the chat. Okay, we're getting near the 5-minute mark. Not getting a lot of questions, so I'm either assuming that people are frantically trying to get it done in the next 30 seconds, or you've just hit next and you're looking at my solution. Okay. If you hit next, you can see what my solution is to this particular problem. I created a class called instrument data. I created a fairly rudimentary init method that allows me to pass in the raw data and save it as a private data attribute. And then I almost literally cut and pasted the 3 functions that I defined into the class. And all I had to do that, to make those work, was I changed the first argument of each of those functions from data to self. And then everywhere in the function that it used the data argument, I changed it to self dot underscore underscore data, so that it directly accessed the class's data or the instance's data. And that's it. That's all you have to do. And then what I did was I had to modify the read instrument data function so that instead of returning this dictionary that I had before, I actually am using that, passing that dictionary in to the init method of my class and having the function return an instance of that class. And now I can try it out. That's not all that different from what I saw before, but now you can see actually using these functions doesn't require me to pass around this data structure anymore. And in fact, the functions are attached to the data itself. But it gives us the same values that we had before. Again, the key takeaway here is that in this particular case, because the data itself was complicated, the function implementations and the data were intrinsically tied to each other. And because that data was not fully self-explanatory, it's useful to hide that data structure directly from the user, encapsulate it in this class, and require that the user interact with that data only via the methods that I've provided. And it makes it much cleaner. This is I think, a much easier way of understanding what's going on. Now, the second example where object-oriented programming can be useful is when you have complicated function signatures. If you don't know what I mean by a signature, that's the collection of arguments that you have to pass into a function in order for the function to work. Now, usually this arises from having lots of different data. Okay, so instead of just having one big monolithic data structure like we had in the previous example, you have lots of little data structures. Okay, and so I'm actually going to go back to that same example that we used in the previous section of this instrument recording values. And I'm just going to look at a different instrument recording that has 4 different variables in it. Same structure, just 4 different variables, A, B, C, and D now. And I'm going to modify my read instrument data function so that instead of returning one big complicated data structure, I'm going to return 8 smaller, easy to understand data structures. Okay, I'm going to return the time and the values of all of these variables as separate things. And so now when I call it, first of all, this line is really long. And getting the order of these right, you better be sure you're doing that right. But it works. And if I try the print data test on any one of these data structures I've just created, I'd say the print data test passes. They're pretty straightforward. They're small, they're easy to understand. Based on the name of the variable, I can figure out, I know exactly what that is. Okay, maybe you could rename the variables or name them wrong and you've missed something, but I'd say it's fairly self-explanatory. So there's no problem, right? Well, let's take a look at what happens when you start trying to define functions that rely on all of these many different individual data structures. I'm going to revive my integrate trapezoid function from the previous section, but I'm going to add a bunch of compute functions that compute new quantities based on the values of any number of these different variables that I've created. And you'll start to notice that a few things are happening. I've started using very, very short names for variables because otherwise, especially in the case of V3, this function signature would get really, really long. And this is all kind of nonsensical operations. But the point here is to show you that when you have lots of arguments to your functions, keeping track of it all can be a mess, can be painful. And you can imagine creating dozens of computation functions like this. And then when you call them, everything works, but look at how long this line is just to call this one function. And would you happen to remember that this function needs the time and then the value and the time and the value? Or would you think, was it value time, or was it all the times and then all the values, so forth? It's complicated enough. You have to look up in the documentation how to use the function, okay? These are hinting at the problems here. The data itself individually satisfies the print data test, but it's so numerous, keeping track of it is starting to get painful. There are so many errors that could come up just due to a typo in one of the arguments to one of your functions, or it could be that you swap the orders. You can't remember which argument goes where. These are all things that become prone to error. And so what would be really nice is to figure out how could I fix this problem, make it so that it's less error prone. And the way to do that is to recognize that all of the data that you have that's being recorded by the instrument and all of the functions that you're computing from that data, all the functions you're using to compute new quantities from that data, rather, they're all essentially measurements of some common thing. The data is a direct measurement of something, maybe the environment that the instrument is in. And the new computed quantities are also measurements, kind of secondary measurements of the same thing. And so what we can do is understand that the functions and the data are conceptually related to each other. And so we can group them together in this conceptual box, okay? This is a little bit more challenging, but I'm going to give you 5 minutes and try it again. Try creating your own class that groups these functions and the data together and gets rid of this problem, this error-prone problem. And maybe due to the fact that we're getting close to the hour here, if I get enough people saying, go ahead and move on, I can go ahead and move on to my solution. Just indicate so in the chat if you'd like me to move on. Or maybe more importantly, if you don't want me to. Okay, I'm getting some move on, and in the I'm not getting anybody telling me please don't. Okay, so I'm going to go ahead and move on. Thank you for the feedback. So the way I solved this problem with a class was I created an environment class, like so. Okay, I have again a fairly simple init method that allows me to supply the times and the values, in this case as dictionaries, individual dictionaries. I made the integrate trapezoid method a private method of this class. Don't necessarily have to do that, but it's kind of nice. If I expected a user to use it directly, then I would go ahead and I would make it public. I made a couple functions in there to actually retrieve the times and the values of a specific variable by request. And then I added the functions as they existed. I just now use either these public get values methods or get times methods, or this private integrate method for all of these functions. So I'm actually using the methods that are in the class itself. And then I modified the read instrument data method as well to, again, this time, return an instance of the new class that I created. And now you'll notice that, first of all, this read instrument to data function call is much shorter because it's returning one thing, an object. And all of these function calls are now really, really short. In fact, some of them don't even have any arguments because all of that data is embedded in the class or in the object itself. But they all work. They all give you the exact same values that we had before. The key takeaway is that when you have a lot of data, numerous variables that are all related to the same thing, keeping them straight can be painful, but grouping them together into a class can be incredibly useful. Okay, I've got one more thing that I want to talk about, and that is some other simple cases where you might want to use object-oriented programming. One is, as we talked about when we talked about the Python data model, if you want to take advantage of the Python data model's special methods, you want to create something that you can do arithmetic on, you need to use special methods, and that means you need to create objects. Another common example is exceptions. You guys are probably familiar with the fact that every time you get an error, an exception is raised in Python. You can create your own exceptions by inheriting from the built-in exception classes in Python. And in so doing, you can actually get a little bit more information to the user as to why an error was thrown. Though I will warn you, you still should use informative text messages, strings, to the user to let them know why something actually broke. And the last is open development. Everything in Python is an object, and that means that there's a lot of object-oriented code out there in the Python world. If you want to contribute and use and understand other code that you're getting from the open source community, you probably need to at least understand object-oriented code. But it's even better if you know how to program it yourself. And that's it. Thank you. Are there any questions? Or perhaps any questions in the chat that didn't get answered? I'm happy to answer them. I apologize for going a little bit over on time. Set. Keyword args let you define default values for arguments. In R, you can do this cool thing where you define defaults in terms of one another. Does Python have something similar? Not knowing R, I'm not entirely sure I know what you mean. Perhaps someone else knows. Okay, example coming. I guess while that example is coming, there was one question from people I noticed in the chat about whether it was a good idea to embed read instrument data into the class itself. That is a choice. You can do that, but there's a principle in object-oriented programming called the separation of concerns. And the separation of concerns here usually refers to aspects of the computation or aspects of what's actually happening under the hood in the computer. And that read data, yes, you could put that in the class, but imagine you have a bunch of different versions of instruments or similar instruments out there that output different formats, the similar data, but in different formats. You'd have to have a different function for each different format. And now your class is starting to become complicated just because of formatting. And that's a different concern. So I would leave the formatting issue to something else. And in fact, right now we only had one format, so one function worked fine. But you could imagine at some point where there were so many different formats for the data that you may actually want to create a class just for that, just for reading instrument data. And then you could say it's this type of format, or maybe figure out an algorithm to infer the format and read it, and then pass that data to the instance, the creation of your other class. That's a separation of concerns. Set, okay, so if you have a circle class, you could define it in terms of its radius, area, or circumference. The constructor would take any of those three for its argument, and there's a way to define the default value for each argument in terms of other arguments. Ah, yes, and it'll calculate whichever of them aren't defined. I don't think there's a way to do that just from like a special method or something like that. Normally, the way that would be handled is you would write that special handling in the init method yourself. So in other words, you might give all of those different things, radius, area, circumference, some default value like none, that's capital N, lowercase o-n-e, right? That's that special thing in Python that represents nothing, literally. And if you did that, then you could see if one of those default values was supplied, it wouldn't be none. And so then you could figure out from what was supplied, well, what do I need to do? And then maybe you could even figure out that someone supplied two things that are inconsistent with each other, and then you'd throw the exception right there at construction time. But yeah, you've got to handle those special cases yourself. And it's usually done in the init method. What's the difference between attributes and method in a class or object? Okay. Attributes can be variables or functions, okay? And if a function, basically the word method is just a synonym for a function owned by a class, okay? And well, I don't know, maybe that answered your question. Do you want me to go on? Attributes is just the generic term for anything owned by the class or object. Okay, so it could be a variable or it could be a function. And if it's a function owned by the class, we just call that a method. Cool, okay. Any other questions?
Thank you again, Kevin. That was a great tutorial, and thank you everyone for your questions, your support, and I think we covered a lot of ground today, so thank you.
If you have any questions going into the future, thank you, Seth. Just ping us at xdev@ucar.edu, and we're happy to help you out.
Okay, look for an email about the next tutorial. Thank you.
Thanks, everyone.